Okay, good afternoon. November 24th, 2025, Fanshawe College, London, Ontario. TELE 1025, telecommunications course. Okay. You should see the course, splash page with my mouse moving. Is that correct? For some reason, I don't see that green outline. Okay, good. All right. All right, let's bring up the topic for today, and it is superheterodyne or heterodyne. All right. Cool. Here's my laser. Here's my presentation. Let's go. So uh, except maybe one lab so far. Well, maybe two, because we did the AM IF amplifier, and we did. We're still we're still in progress with doing the frequency modulation lab. If my voice is coming too loud or too quiet, please let me know. Because the last time it came too quiet on the recording. Um, both of those labs, the AM, we also did the AM modulation, but with the AM modulation, we concentrated mostly on the transmission part. With the FM modulation, when the AM IF amplifier, intermediate frequency amplifier, and we're going to talk about that today. We did part of that receiving concept there just by concentrating on certain frequencies with the tank circuit, by getting the resonant frequency of the tank circuit. So that's that part would be something also that's associated with the receiving of the radio frequency signals. And if you remember when I grabbed that little clock radio from the back room and I just put that on top of our breadboards, we were able to hear the 1 kilohertz tone through the radio when we tuned to that particular frequency on the AM with the AM. But later on, we actually plugged in some music as an input instead of the function generator. And if you noticed, you couldn't help but notice that the signal that was coming out through the radio was not that clean. There was all kinds of other things present with that music thing. So today we're also going to tackle some of the ideas that are associated with that. Okay, just gonna make sure that we are recording. I do have the option to stop recording, so we must be recording. Cool. All right, so today's topic is the superheterodyne receiver. What is the concept of this whole concept? Okay. Well, the superheterodyne is using frequency mixing to convert a received signal to a fixed intermediate frequency, and we represent that thing with the designation of IF. So the IF, when we have those sentences, we're going to read some of the sentences today. This is not if, that's IF, okay? Intermediate frequency. The concept of heterodyning, heterodyning is basically mixing, combining two frequencies on a nonlinear device, in our case, and coming up with, well, the outcome frequencies that would be the sums and the differences of the frequencies that were introduced to the device. Right? So again, it's using frequency mixing to convert a received signal that's coming from the air, and we're converting that frequency to something else that's an intermediate frequency. So we are something like translating one frequency into another. Right? We are changing the carrier. We're still keeping all the information and all the proportions and all the amplitude or all the frequency modulation or whatever other modulation there is, except we are switching, well, railroads, if you can say that. We're switching the gears. We're translating one carrier into another. Why would we want to do that? And this presentation is about that also. Oh, wow, here, reasoning. Okay, I wrote that yesterday. The most common, if you look at the past, the most common type of receiver before the SuperHeterodyne was something that was called TRF, which stands for Tuned Radio Frequency Receiver. And we use that to pick up a specific radio station, right? And to pick up receiving specific station, because in the air there would be a bunch of stations present, hence the word broadbanding. So in the air, all the frequencies are in the form of broadband, which is a wide band of space that contains all frequencies and all the channels at the same time in the same space. All right. All right. So to pick up a specific radio station, a receiver needs two main things. Well, it needs selectivity. And selectivity, in our case, is the ability to single out the weak signal of the desired station, because those signals are weak in the air. So it's the ability to single out or catch, in the layman's terms, a weak signal of the desired station from multitude of other radio signals, which are at different frequencies, and all those hit the antenna. So we need to be able to pick that one that we want. So we need to have some good selectivity that we want to pick up the one that we want to listen to, and well, in case of radio, and ignore all the rest. And if we decide to change the station, we do the same thing, change the station to another frequency and ignore the rest. So we need to have selectivity. And we need to also have something that's called amplification, and that is basically the ability to boost the weak signal, the weak selected signal, to a level strong enough to drive speaker or headphones, or to produce the desired output. All right, so all of a sudden we hit some sort of hurdles, and one of them is called a multi-stage problem. And let's see what this is about. In the TRF receiver, and remember, tuned radio frequency receiver, that was the old ways of doing things. In a TRF receiver, both selectivity and amplification were achieved across multiple stages, usually using vacuum tubes or transistors. Each tunes to the exact same frequency. So there will be multiple stages. The signal has to pass through multiple stages, and every stage had to be tuned separately and all together to that desired channel. well, tuning coils. Each stage contained a tuned circuit, well, a coil, and variable capacitor, and those were responsible for selecting the desired frequency. So that's, remember when we're doing the tank circuit in the Class A amplifier. So it's pretty much comes down to something like that in one form or the other. All right, so the first stage would provide the modest amount of frequency selection. So the first stage, we would just lock onto that frequency. So more or less, we are tuned into that frequency as much as we possibly could. The signal would then pass through the second, third, or even fourth stage sometimes, where the process was repeated to achieve the necessary overall selectivity and the gain. For the receiver to work correctly, the variable capacitors in every single one of those stages had to be mechanically linked and adjusted simultaneously and identically. And we'll see how that was done. This process was called gang tuning. Right? All right, so a little bit of a thing going on here. The TRF receivers were the dominant commercial technology from early 1920s until they were largely superseded by the SuperHeterodyne design. Sometime in the mid 1930s, keeping in mind that the SuperHeterodyne was invented in 1918. So see how long it took for the change to actually be available for us regular people, because first it was developed for the military. While the SuperHeterodyne became the standard for higher performance radios, TRF technology persisted in inexpensive or simple radios, with some versions still being manufactured into the 1950s and even later in certain applications. And here's the reference. The transistor was invented in 1947. All right. So then, well, that's why it's vacuum tubes or transistors. And if you look at some of the dates and stuff like that, you might say, okay, this transistor was invented in 1947, and the superheterodyne was invented in 1918 and then implemented in 1920s, 1930s, so something doesn't add up. Well, it's because the technology was not implemented right away. Yeah. All right, so continuing with the multi-stage problem here. All right, so here is the first stage, second stage, and so on. As far as the signal hits the antenna, so there's a modulated carrier hits the antenna and is being picked up. And the first RF amplifier, RF radio frequency amplifier, would have to have somewhat of selectivity in order to actually lock on to that carrier that is present among all the other carriers within the air. Then would be the second stage of the second RF amplifier, and that would just pick that one up and clean it up a little bit and pass it along. And here is the detector stage, and that detector stage also had to be tuned to that specific carrier that keeps going, and that carrier is the same thing. If it was a, let's say, 1,000 kilohertz coming in. So in this here, this one is concentrating on the 1,000 kilohertz carrier. This one is concentrating on the 1,000 kilohertz carrier. And this one also is 1,000 kilohertz, 1 kilohertz, or whatever, the same frequency. That frequency is same present, same carrier here, same frequency of the carrier is present in the detector. And so detector is interchangeably used with the word demodulator, right? So all those had to be tuned properly, and that required somebody who was trained in the ways of operating the radio. So look, you have one 2, 3 dials here, that all of them have to be adjusted properly in order to lock on to that station or radio station that you wanted to listen to. And for the most part, that was done within the military environment in the beginning. Most, like a lot of technology, new technology starts with the military uses. All right. Later on, let me see here if I can just jump onto one of those here. You see, here's another example of that type of a TRF radio. And over here, you see, what does this thing say? Tuning all three stages of TRF said in unison. This 1925 receiver, Grape Synchrophase receiver, sounds like some of those commercials, late night commercials of some devices, cleaning devices and all that stuff. Has thumb wheels instead of knobs, which can be turned with a finger, so a third hand is not needed. See here? This person can just kind of like develop like a wrist action for simultaneously tuning all three stages, as opposed to here. All right, you will have to tune. So there's a bit of a, the receiving of the radio signal was by all means possible in 1920s, but it was not as simple as today. All right. Okay, move on. What is the reasoning? Well, the reasoning was the tuning difficulty, and the reasoning for what? The reasoning for the superheterodyne, which is, we stay on topic here. So, mechanical complexity, all right? So, manufacturing the ganged capacitors or multiple variable capacitors on a single shaft, you could do that with the required precision, so the values tracked. So tracking is the term that we also got to remember. To track perfectly across the entire tuning range was that involves some sort of mechanical talent of the engineers to come up with something like that. So you could have one single knob maybe or dial and turn all three of those stages here. You could just put maybe elastic band around, but it doesn't work that way. All right, so then there is imperfect tracking, okay, which is basically tracking or looking for that signal, tracking that signal. If the tuning across the stage didn't match perfectly, be a tracking error, the receiver would lose the signal, sound would be muffled, or lose significant amplification as the signal moved out of tune with the later stages. All right, so what's the variability? Say the performance, selectivity, and gain would vary significantly across the broadcast band, often being much better at one end of the band and not the other. So if you move to that side of the dial, you could get some good selectivity, and if you move to the other side of the dial, the selectivity would be somewhat compromised because of the problems that mentioned here. Right? Usually probably due to some mechanical complexity. If those dials had to be turned, each of those had to be turned slightly different at different rate to achieve the same selectivity in all those stages here. So that's ganged tuning, because these three are ganged. Okay. All right, the SuperHeterodyne solution. SuperHeterodyne circuit invented by Edwin Armstrong in 1918. It eliminated the complex ganged tuning problem by performing most of the selectivity and amplification at a stage at the single fixed frequency. So instead of the concept looking like this, we have, let's say, 600 kilohertz or 1000 kilohertz comes in here. That 1000 kilohertz reach this, again, repeating that, and the same 1000 kilohertz hits this stage, and the same 1000 kilohertz hits this stage. And those three separately have to be tuned to that carrier. Well, things have changed a bit with the SuperHeterodyne, or the mixer, right? Was invented, a frequency mixer. So what do we have here? Forget this little square here for a couple of seconds. We have the tuning to whatever the station is being broadcasted over the air. Among other ones, we want to tune to that specific one. So we tune that RF amplifier, first RF amplifier, right to that one. Then we hit something mysteriously called a mixer, and then another mysteriously kind of a named IF amp, intermediate frequency amp. And then we have the demodulator and audio amplification to strengthen the signal that we have demodulated. Remember? See, here's the detector, demodulator. Same thing, just sometimes it's being named this way or the other. And then we have even something more mysterious here. It's okay, LO stands for local oscillator. Okay, let's take a look at what's going on here. All right, just the architecture of the whole system, of the SuperHeterodyne system. Antenna captures the signal, RF amplifier, slight boost, and pre-selection. So it selects, does the first triage of the signal. Yeah. Here's the mixer and the local oscillator. It says shifts the frequency to if, right? Shifts the frequency to IF, shifts the frequency of what? Shifts the frequency of that carrier. What carrier? The modulated carrier, which means the carrier with all the information that's modulated onto it. It shifts to the IF amp. Now, let's not concentrate. Let's forget that filter for a sec here. Ideal situations don't need filters, right? But we actually do. So there's certain kind of RF station or RF signal, radio frequency signal of certain frequency of the carrier, passes through the mixer, and something is injected into the mixer as well. And obviously something is getting mixed, and all of a sudden we have something that is called the intermediate frequency. Then we have the IF amplifier already. The IF, intermediate frequency, comes out of this square right here. And whatever comes out of there, it's at every single stage, there's a little bit of, okay, I received the signal. Who did this? Let's do some rough edges. Let's clean it up a little bit. Okay, clean it up, amplify it, pass it along. Right? So that's what that does. And here's the detector, extracts audio, and audio amp drives this loudspeaker here. All right. In more detail. RF amplifier, not always present in cheap stations, radios, sorry. Crucial for high quality. Well, there's some statements. Improves signal to noise ratio. So that's how this one cleans it up. Provides initial selectivity in order, by rejecting strong interference before it hits the mixer. So it grabs that weak signal, cleans it up a little bit, passes it on. It in kind of semi-good shape. So all the content is there, but some of the interference is still there, but we'll take care of that as we go along. So it passes on to that. And here's the local oscillator. Ooh. Here's the mixer, nonlinear device. Remember, the nonlinear devices produce sidebands. Okay? It multiplies the RF signal, yeah, with the local oscillator signal. So we have a frequency that's coming in. Over here, there's some sort of mysterious frequency that's coming in there to produce something else that this one wants to see. So out of this frequency and that frequency, what do we have on the output of here? Well, we do have the sum of the local frequency oscillator, and just this one just gives a frequency, a sine wave. That's all it does. So we got the sum of these two. We got the difference of these two. This one minus that one here. This one here minus that one. Local frequency oscillator. Here's the LO frequency, and here's the RF frequency with something that's called a high-end injection, which is the usual case. In order for us to translate this kind of carrier into something else, into another carrier, so whatever the carrier is, we want to convert that into one type of carrier. And this frequency of this carrier, the intermediate frequency carrier, after the translation of the frequency, it's just putting that information from one carrier onto another carrier. And why would we want to do that? Right? Again, why? All right. So it produces sum and the differences with the high-end injection. The local oscillator injects a frequency into the mixer. We're interested in the difference of that. This minus that, right? The local oscillator frequency minus the original coming in RF. And that's usual case that we do the high-end injection. Now, in some specific cases, maybe within the microwave regions, we might want to use the low-end injection. Because the sum of this frequency here, so here's difference, this one minus that, or this one minus that, or this one plus that. The reason for that is that lower frequencies, because microwaves frequencies are higher than the VHF region, it's just easier to generate stable lower frequency than the higher frequency. Within the VHF doesn't matter. So keep in mind that in order to mix things properly and get what we want on the output, we can use the high-end injection or low-end injection in order to get that. Because the sums and the differences are going to work out into producing something that we can concentrate on, we can grab and reject all the others, sums and differences. So when it comes to high-end injection here, we only keep the difference, intermediate frequency. With a high injection, IF stands for intermediate frequency. All right. Local oscillator. Now, here's the idea. IF, the intermediate frequency, must be kept constant. Whatever the frequencies are coming in here from the outside, we want to convert them all into 455 kilohertz for the AM system, amplitude modulation receiver. And we want to convert to everything that comes in there to 10.7 megahertz if we're talking about the frequency modulation FM radio. So those two IFs are different, but with AM, it's always going to be here. We're only going to work with the carrier of 455. If it's FM, we're only going to work here with 10.7. So again, for the third time, I'm asking myself a rhetorical question that says, why? All right. We keep going. Here's the IF filter, amplifier input. IF, intermediate frequency stage, the circuitry that follows, this is the circuitry that follows, all right, can be optimized for maximum gain and selectivity, as the signal has now been converted to a fixed frequency. And here's a little statement here. The IF stage handles 90% of the work in rejecting undesired nearby stations. For the fourth time, I'm asking, why bother? Right. Now here's the demodulator detector, same thing. Removes the high frequency carrier, so it just strips off the carrier and keeps the audio signal. So from that point, we have the audio signal, somebody talking to the microphone or music playing. We don't need the carrier anymore. The carrier, we just needed that to carry the intelligence. Once we get the intelligence here, we can just throw out the carrier and keep the intelligence because that's what we're interested in. Then the audio amplifier boosts the weak audio signal to the level that can be used to drive whatever we need to drive that with it. Okay. Then there's I just want you to know the concept of the AGC, right? Automatic gain control. And there are different types of, it can be used at different stages. It could be used at the IF stage or in the audio stages as well. Automatic gain control. It's a signal feedback system that if the signal is too loud, it's going to bring it down automatically. If the signal is too weak, it's going to bring it up automatically to the constant level that we want, so we can work with later on. Okay. So, for the fifth time, I'm asking the question, why do we want to bother translating one frequency into another? Can we just be normal like everybody else, and do this when we listen to a radio? All you have to do is turn all these knobs so they're turned to the same station. Because we have to turn all three to the desired station. Any of those will do. Here, it's the slides. When we have to do the selectivity and selectivity of what we want and rejection of what we don't want, all these here would have to be capable of working well with all the frequencies that are available for that band, whether it's AM band or FM band, from the lowest type of carrier to the highest across the other side of the dial carrier. So, of course, with the reality of things, every piece of equipment has its own sweet spot that works at the best or the bestly. Okay. Then it is going to suffer on one end, maybe suffer on the other end. So that thing would have to be optimized. So there would be some preferences of which frequencies to use for the radios that are better than others as far as selectivity and quality of the whole transmission system. And in this case, so that was that case here. All those had to be adjusted. In this case, we pretty much only have to adjust one knob right here. We just adjust. This is where our tuner dial is in the local oscillator. We changed that frequency that is being injected into the mixer. So it is going to give us the difference between it and whatever is out there that we're going to hit. And it's going to convert that to, let's say, 455 kilohertz for AM. Now, when we only have to work with all the rejections, so over here, this one here is bring them in, all right? And over here, once you brought them in and clean them up a certain way, we'll process them. Now, it is so much easier to design and accomplish a circuitry that only has to be the best at processing only one frequency, which is, let's say, 455 kilohertz for AM and 10.7 megahertz for FM. So it's easier to design a circuit that works well with that specific carrier. The filters can be adjusted properly, the levels can be adjusted properly, because all there is, it has to do is just be really good at processing one carrier. And that's when the quality of the whole transmission goes way up, when we only have to concentrate on that one carrier here, which is the IF carrier. So here's the idea of the heterodyning or the superheterodyne. Get whatever comes up before it gets processed further, convert that into that IF frequency. And then here, things can be nicely selected, nicely rejected, nicely processed, and reproduced for the intelligence, for whatever it is. In this case, it would be loudspeaker. Advantages for the superheterodyne. The superheterodyne design replaced the tuned radio frequency receivers and now it remains the standard due to what? Well, good selectivity, excellent ability to separate stations that are close together on the dial. So selectivity goes way up, which is good. Sensitivity, high gain is easier to achieve at a fixed frequency, which would be the IF here. And of course, the stability, fixed IF tuning, the fixed IF, because that IF is fixed, eliminates the risk of the receiver oscillating unwantedly. Crystals can be used to get to get stable frequencies because we don't have to change those. So selectivity, sensitivity, stability, well, the ease of use. You don't have to be trained radio operator anymore all of a sudden. Now, everything would be so beautiful but everything would be so beautiful if there were no challenges, but the real life always presents some real challenges, and the challenges are of the reality. Okay. Here's the concept of a ghost station. Mixer creates the sums and differences on given frequencies. Two different incoming frequencies can produce the same IF. All right. I put the accent in the wrong spot. Two different incoming frequencies can produce the same IF. Not only the one that we want. It could be the one frequency of station that we want to listen to, but there could be some other frequency that also can give us the result of the same, let's say 455 kilohertz. For example, IF, the IF frequency of the 455 kilohertz for the AM receiver, and let's say the local oscillator is dialed manually or automatically to produce 1455 kilohertz. Well, two different stations can be picked up by the combination of that. It could be a 1000 kilohertz. Let's say this is the one that we want, which would be that local LO frequency, local oscillator frequency, minus that. But if there is another frequency of the 1910, for example, present, subtract 1910 from that, it also is going to give us a frequency beat of 455 kilohertz. There's a little bit of a problem there, right? Okay. There's a problem, there's a solution. So they got together and they came up with a solution. The unwanted 1910 kilohertz frequency is called the image frequency. That's just the terminology that was chosen for that. Well, a tuned RF filter or preselector can be installed before the mixer in order to eliminate the image frequency. And those are far enough apart that can be eliminated and only this one kept. There's a problem, there's no problem. Modern use. When it comes to heterodyning or superheterodyning. Superheterodyne concept is present in all radio receivers, from the wooden radios of 1920s to the smartphone in your pocket. It all has superheterodyne. See, you own one. You own one right now. Applications, there will be of course, AM and FM broadcasting. TV receivers, they also use intermediate frequencies. Radar systems, satellite communications, mobile phones, and GPS, and whatever transmits and receives, the receiver is most likely is going to be super heterodyne type of a receiver. Why? For the seventh time, well, here's the answer. So we don't have to use three knobs. We only have to use one. All right? We already had seen this. And we don't even have to use knobs if you don't want to. I just kind of was carried away, and I asked the AI to come up with um, with this. What do we have here? Well, we have the Siri, we have the Alexa, and we have the Hey Google thing, right? Shouldn't be saying that because something can get triggered. Uh, you don't even have to turn any dials. You can just tell what radio you want to use, listen from the whole entire world. Only radio, or you can ask a question, philosophical question. So from this or this here to this. And from a philosophical point, it just makes me wonder, were we as a human society happier then, or are we happier now? I'll leave that up in the air. Helpful materials when it comes to the SuperHeterodyning. I found one video. You're welcome to watch that. It's not by me. I just found something on the internet that is going to sort of reinforce what I just said. So I placed it there. Why not? So you don't have to search for it. Let's see a couple of examples here. Example 1. Carrier is an amplitude modulated signal of, modulated signal. A carrier is an AM signal, and the modulation is from 300 to 3000 hertz, which is a voice signal. What's the minimum 3 dB bandwidth needed for the intermediate frequency? Okay, here's the solution. I'm pretty sure you're biting your nails waiting to know that. The minimum requirement bandwidth for standard AM signal, which was both sidebands, is twice the highest frequency present in the modulating signal. All right, so we just do simple math. Using the maximum modulation frequency, the maximum modulating frequency is 3000 hertz. So that's as far as those sidebands are going to stretch. Multiplied by 2. And what do we have? 6000 hertz, which is twice as the highest modulating frequency present in the signal. And I said something here. Oh, yeah, by the way, here. As far as bandwidth requirements, and the reflections or conclusions here. I'll tell you why not. The bandwidth is required to transmit that signal is 6000 hertz. For example, for the AM. And the 6000 hertz is required whether that thing is on a carrier that is coming into antenna. So it's a somewhat tricky question. That's coming into antenna, or same bandwidth is needed for the IF, intermediate frequency. Intermediate frequency is nothing else except that information that is on the one carrier, we are putting into another carrier in order to make easier the construction and maintaining and blah, blah, blah. Effectiveness of the processing equipment that has to clean up that signal. It's easier to make that. And whether that 300 to 3000 is on that carrier, or that carrier, or that carrier, or the IF carrier, it still needs the same bandwidth to transfer 300 to 3000 kilohertz. So here's that I kind of put that thing on here, so we get this. Now, as far as because there are problems with the image frequencies. Remember what the image is? The image station or image frequency is the frequency that can also produce the same intermediate frequency. So if there was another station nearby of different frequency, but it hits that specific frequency, then there could be a problem because both of them could be biting each other. Where is that also important? Because, well, the problem with the radio stations can be easily solved because you just have to separate geographically the transmitting radio stations, broadcasting, music or whatever. You just have to separate them geographically, put one in one city, 100 kilometers later, put some other one or whatever, right? So that can be, plus some of the selectivity can be done at the front end stage, anyways, just if there's something there. But also the problem would be, let's say, in the audio environment, specifically stage audio or pro audio. And it had to do with wireless microphones. Sometimes you have one person that sings on the stage. You get them the wireless microphone, no problem. But what if you have a whole bunch? That's all of a sudden you need 12 or 24 wireless microphones. Well, those microphones, each wireless microphone will have a different carrier that transmits from the belt pack where the microphone is connected to the receiver that is connected to the mixing board. And not that type of mixing board, the frequency mixing board, it's the audio mixing board. So those frequencies of the carriers that belong to each and individual wireless microphone that's being used on the same stage, which will be with the same physical proximity, they have to be brought together or used in the same system or in the same proximity in a way that they don't hit the image frequencies that could make one wireless microphone interfere with the other. And if you go to the music store and buy a bunch of those, then if you buy 3 or more, or more than one, you just have to make sure that, and don't have to do any calculations. There will be just like a list available probably on the internet or provided to you that these two microphones, yes, they can be used together on the same stage, but those two, no. Okay, so let's get this in here. Determine the image frequency for a standard broadcast band receiver, which would be the AM. We can tell that it's AM because it's standard broadcast, and standard broadcast is both the sidebands present. Plus, we see the 455, which applies to AM, and this is the IF for AM. We have IF for AM, right? Intermediate frequency for the amplitude modulation. If we're tuned to the 620 station, 620 kilohertz station, 620 kilohertz station. So what frequency should we not have? Or what other frequency could create a problem in a way that could also result in 455 kilohertz, which would, and if there's any information on that one, that information, those two carriers would just bite each other or be in conflict with each other. All right, so let's see here. The first step is to determine the, and this is basically from the textbook example here. The first step is to determine the frequency of the local oscillator. So LR minus, what is it that we have to subtract from 620 is going to give us, because that's the difference we're interested, LR minus the carrier. And that is going to be, so what is the local frequency oscillator? So the local frequency oscillator is 1075 kilohertz. By the way, how is it that the local oscillator knows how to adjust? There are different ways of doing. Well, first was the mechanical way, the old way, 1920s way. Then there's also a mechanical solution that those capacitors and coils could be put on a single shaft. And so if you turn one, the other ones turn. Or you could come up with some sort of VCO, voltage controlled oscillator. So if we can have that implemented, and to be honest, quite often, more than not, there are certain microprocessor units by doing digital kind of controls. Then that LO is going to get proper frequency to tune into that station. Just remember, in order to tune this to this whole receiver into whatever station that we want, all we have to do is turn this. Got the one? Yeah. So by that simple equation, because we are interested in the difference, where's that here? Yeah, we're interested in the difference. This minus that. Okay. That's what this one is looking for, the IF. Which, like I said, the difference between this and that has to give us the 455, because 455 is the only thing that this thing is going to see and work with. There we go. So by that, we accomplished that by rearranging the equation, we can just, come up with this frequency. So now, now we have to determine what other frequency, when mixed with that, is going to give us that. So we just step up. So what would be the other frequency that from that you subtract that result here? It's going to give us that. So simple equation, rearranging things. So the image frequency for that one that would be of significance would be 1530. So that has to be tuned out. But look, 10 kilohertz, well, 1075 kilohertz, 15 kilohertz. You got 5 kilohertz, or sorry, 500 kilohertz. So you can do something with that, because this one here is far enough from that one that you don't have to strain too much. Coming up with a filter that would reject that would not be too complicated procedure. Another example. Is that the last example? No, we got one more. All right. Here we have a diagram here. 20 minutes. That's okay. So we're dealing with the FM right now here, right? Something interesting. We take this down and we take this down again. So we translate, we do it's like a staging. staged uh, heterodyning. We have two. We can say you have two superheterodynes, one after the other. First, we bring it down a little bit, and then we bring it down even more, and that's what we're working with. Whereas if we just did one, some of the rejection of certain frequencies that are adjacent would be more difficult. So if you bring it from high up there to somewhere lower, and then again to way low, far away from all that stuff, and if you then it's going to be even easier to come up with a high quality circuitry that does the selectivity, because at this point selectivity is almost non-issue, and of course the rejection of something else that could be wanting to bother us as far as imaging or image frequencies. All right, so with this one here, determine the image frequency for the receiver illustrated in figure 6. Well, this figure here, 6.8. All right, and this is from the textbook. Here's a reference. Okay, the image frequency is one of the when mixed with 30 megahertz. So here's the 30 megahertz local oscillator. Minus that is going to give us 10 megahertz. This minus that gives us 10 megahertz. And determine the image frequency. So we have 10 megahertz. What else? So the 10 megahertz gives us something higher mixing with 20. So 30 and 20 gives us 10. What else can we go stepping up? That's also going to give us 10 megahertz will be the image. So, we'll take 10 more here. 40 minus 30 also is going to give us. So the 40 megahertz. Do we have it here? So, oh, yeah, there it is. 40 megahertz is also going to give us 10 megahertz. So if there's any station that was in 40 megahertz band and has some information, so those two channels might start producing some funny things. But then, so that's here. That will be the example here. That will be the answer. 40 megahertz. Then later you take even down there from that, sort of upper, and you go with 11 megahertz minus 10, and that's going to give us 1 megahertz. So all of a sudden, from 10 megahertz, you translating that into 1 megahertz. That 1 megahertz is far enough from all these 20 megahertz and all this 30 megahertz and 40 megahertz business that the selectivity and rejection of all the unwanted stuff is much easier. So that's why staging is kind of not staging of the house, but having different stages. Oh, there's one more. Who would have guessed? Also about the image frequency here. Determine the image frequency for the receiver illustrated in this here. Okay, determine the image. Okay, what do we have? Without looking at this here. All right. What's going to be here? 21 minus 20. It's going to give us 1. What unit? Megahertz here, megahertz here. So 1 megahertz. Okay. So what also, so this minus that is giving a 1. He's giving us 1. So what else minus this is going to give us also 1 megahertz? Well, 22 megahertz. Huh? And that's the end for this one here. Do you guys want to continue with the fiber optics second part of it, or do you want to take that during the in-person class on next Friday? I'll leave it up to you. How was your day so far? Are you able to absorb any more, or would you rather shift it to the Friday lesson because maybe you're beyond and the receive? Yeah, leave it to Friday. Okay, because I could just be talking for another hour, but what's the point if I keep talking if you're not able to absorb the information? That would be just that would be unfair. Cool. So that's it. That's all she wrote, or he wrote, back road, back road, back roads for today. And we're continuing with the frequency modulation lab. The quiz is already introduced. It's out and about. So just do that. Then we're going to have not too short from that. We're going to another test. It's going to be the same way that the quiz, except there's going to be more questions and there'll be worth more of the whole weight of the whole final grade, just like the last time. Cool. Thank you for your attention, and I'll see you sometime during the week, probably Thursday and Friday, whenever the lab is. It's Mr. Bucks signing out. Oh, what did I do?